So for the benefit of the recording, I realized that the red-black sets, which I've talked about before, provide an interesting container, which is not the same as set theory, and provides a concrete model for FM set theory, which is a set theory with atoms. And set theories with atoms are used in the Gabai and Pitts approach to modeling binder kinds of relationships, like the new binder in the pi calculus or lambda abstraction. Gabai and Pitts are the sort of principal investigators who discovered this approach. Their theoretical work has been implemented in Alpha Prolog and Fresh OCaml. So if you're interested in those things, I recommend taking a look at those resources. They're quite enlightening. There's also Clauster's work on nominal Levier theories. What is an open question, at least for me, and I don't believe that Clauster addresses this, is whether or not you have the same sort of monadic correspondence. So Levier theories correspond to finitary monads. And the question is whether you get the same kind of correspondence with these nominal Levier theories. So just as a refresher, I'm going to give a simplified presentation of red-black sets. So the idea is that we're going to have two isomorphic copies of set theory that are intertwined with each other. So red sets will be comprehended by red braces and inspected using the red element of relation. Now, what can go inside the red braces are either red sets or atoms. So that's just like Frankel-Minkowski set theory. But the trick is that the atoms of the red sets will be the black sets. So black sets are comprehended by black braces and can contain black sets or atoms, but the atoms are going to be red sets. So then, just to make this a little bit more concrete in terms of examples, if we let red U be the universe of all the expressions generated by this this grammar, and black U be the language generated by the expressions in this grammar, then we can see that the red empty set is in U, and the red set containing the red empty set is in U, and the red set containing both the red empty set and the red set containing the red empty set is in U. So for example, this gives us a red copy of the von Neumann approach to the natural numbers, modeling the natural numbers in set theory. Oh, whoops. There was a, sorry, the OmniGraffle's been doing funny things. Fix this. So notice also that all the black sets show up. And so this is the set containing 0, the black 0. This is the set containing the black 1, and this is the set containing the black 2, and so on. So these are distinct from these sets above, right? And you get isomorphic copies of these things down here. So you get the black version of the von Neumann model of the natural numbers. And then these are just, you know, the set containing the red 0, the set containing the red 1, the set containing the red 2, and so on. Now, notice that in general, the type signature for the two membership predicates, it'll take in the first argument either you know, something from the red universe or the black universe, but in the second argument, it will be red. So this color will match this color. And given those two arguments, it will then produce a Boolean. And likewise, the other way around. So this color here will match the color in the second argument for the predicate. So notice that for the red set, for the red element of relation, putting the black a black set here is a type error, and vice versa, right? Putting a red set here for the black element of relation is a type error, right? So these really are different than set theory, right? It's a different connective. Now here we get therefore two copies of the standard logics. So we'll have a red true and a black true. We'll have a red negation and a black negation, a red conjunction and a black conjunction. And then I'm sort of still tinkering around with a formula that allows for the construction of sets in terms of the structure of atoms and things like that. But the idea is that you want to allow for recursion, and this will be a greatest fixed point kind of construction, just the way I did in the namespace logic. So I'm still tinkering around with it, so I haven't given the definition here, but you can kind of imagine how this goes, right? So this is going to it's going to be the greatest fixed point of all the sets that satisfy this specification, where these are formulae, and this is a specification for the structure of black atoms, right? And this is a specification for red sets, right? So so that's the basic idea, and then but we also get sorry, hang on a second. We also get a model of the nominal formulae, like we find in Gabai and Pitts or Kyrace's work. So I'll maybe next week I'll show what those formulae look like, or you can certainly look it up and you can see that you can give an interpretation that way. The important and with the nominal formulae, we begin to see that this logic is actually quite distinct from ordinary Boolean logic. I mean, it's already starting to look distinct, but it looks like there's just two copies, and then the copies are mixed together here. So that's one way to think about it. But once you start adding the nominal phenomena, you begin to see that this really is a very different logic with a different kind of expressive power. And so again, the point of this example is to show that the container has a strong influence on the kind of logic that we begin to see, in addition to the structure having a strong influence on the kind of logic we begin to see. So, you know, Mike and I are doing lots of calculations with more complicated containers, but I wanted to show that these kinds of containers they yield an interesting family of logics that say new things. So this is a new conception of a container, that's very close to set theory. It's like a cousin of set theory, but by the same token, is not the same as set theory, and it yields a logic that's very close to Boolean logic, but is not the same as Boolean logic. So any questions about this?
In your first slide, when you you're showing examples of empty sets, and in the case of red,
here's one empty set, right? And here's another one. But the rest of the sets are not empty. So this is not an empty set, right? This is the set containing the empty set. And this is the set containing the empty set and the set that contains the empty set. But there's a further distinction, which is that the red empty set is not the same as the black empty set.
And inside we can have any combination, right? Because
you can have, yes, but the important thing is that the element of relation cannot see into inside sets of the wrong color, right? So the red element cannot look into a black set, right? That's a type error, right? And black element of cannot look into a red set. That's a type error. Now, notice, just to expand this a little bit, there's nothing special about two colors, right? We could have red, black, and white. And you could have them set up in a circle or any number of combinations. But so you could have red sets and black, and then here in you could have black sets, and then the atoms would be the white ones, and then for the white ones you would have white sets and red ones, right? So you get a cycle like that. So then you get three different kinds of empty sets, right? The red, black, and the white. Does that make sense?
Yes. I'm also thinking in the next slide, when you have formally specified, this is the only real difference, right? When we have both colors in the recursive definition.
Yeah. Oh, it did it again. Yeah, OmniGraffle is doing weird things. Yeah, that's correct. But there's another difference. So if you look at Kairos' formulae for the nominal phenomena, or Pitts and Gabai's formulae for nominal phenomena, we can model those as well. So and you know, I just started working on this stuff yesterday to write it down, so I didn't get a chance to put all of that stuff in, but because I only just had the observation the other day that that this is a distinct kind of container. In fact, there's a whole bunch of there's an infinite number of these different kinds of containers, and I knew about that for decades now. I've known about this since 2005. I knew about the fact that there are these new kinds of set theories. But I hadn't put it together that I could run OSLF on those new kinds of set theories and get new logics. So yeah. So anyway, so that gives you that starts to show off some of the coolness of the OSLF program without having to go too far astray of set theory. Just like just next door. The set theory next door. Any other questions? All right. Well, that's all I have for today. If there's no other questions, then we can give people back 40 minutes and I'll see you in the dev stand-up. Thank you so much.
Thank you.
Thanks.
Thanks.